For nearly 3 decades, physicists were almost unanimously confident about one specific thing that would happen when Voyager 1 finally reached the edge of the solar system. A very specific type of particle, one that had been theorized about since long before Voyager even launched, was supposed to spike dramatically the instant the spacecraft crossed a boundary called the termination shock. Every model said so. Every prediction agreed. And when Voyager 1 actually got there, that spike simply never happened. One of the scientists analyzing the data put it about as bluntly as a researcher ever puts anything, saying the finding had the potential to turn 3 decades of research completely on its head. This is the story of the first wall Voyager 1 ever hit at the edge of our solar system, a boundary that behaved so differently from what physics predicted that it forced an entire field to reconsider one of its most confidently held assumptions. Stick around, because this discovery happened years before Voyager 1 even reached true interstellar space, and it's honestly one of the stranger episodes in the entire mission. And if you want to catch every new discovery, this incredible spacecraft keeps turning up, go ahead and hit follow before we get into it. To understand why this particular wall mattered so much, you first need to understand what a termination shock actually is, and why scientists were so confident about what would happen there. The sun constantly blows a steady stream of charged particles outward in every direction, known as the solar wind, and for most of its journey outward through the solar system, that wind travels faster than the speed of sound within the surrounding plasma. But eventually, as it pushes farther and farther from the sun, the solar wind runs into resistance from the material of interstellar space, and at a certain point, it's forced to abruptly slow down from that supersonic speed to a much slower subsonic pace. That abrupt slowdown creates a shock wave, similar in basic principle to the sonic boom created when an aircraft crosses the speed of sound, except on a scale spanning billions of miles. Scientists called this boundary the termination shock, and it marks the beginning of the outermost layer of the sun's protective bubble, a turbulent region known as the heliosphere. Based on decades of theoretical work, physicists had built up a strong, specific prediction about what should happen to certain particles right at this shock. A category of particles known as anomalous cosmic rays, essentially interstellar material that drifts into the solar system, becomes ionized by solar radiation, and then gets swept back outward by the solar wind, was expected to get dramatically accelerated exactly at the termination shock itself. The shock was supposed to act almost like a particle accelerator, repeatedly bouncing these charged particles back and forth across the boundary and pumping them up to extremely high energies in the process, a mechanism called diffusive shock acceleration. This wasn't a fringe or speculative idea. It was, by most accounts, close to a scientific consensus, built on solid theoretical grounding, and considered one of the most well-established predictions physicists had going into the encounter. Voyager 1 finally crossed the termination shock on December 16, 2004, at a distance of just over 94 astronomical units from the Sun, becoming the first spacecraft in history to reach this specific boundary. And almost immediately, the data coming back didn't match the script. Instead of spiking dramatically right at the shock crossing the way theory predicted, the intensity of anomalous cosmic ray helium simply didn't peak there at all. University of Maryland physicist Matthew Hill, one of the scientists analyzing the results, explained just how significant that absence really was, noting that the finding suggested the actual source of these particles wasn't located in the specific region of the shock where Voyager 1 happened to cross it, directly contradicting what had been close to unanimous agreement among physicists beforehand. Hill's assessment of the implications was direct. He said the result had the potential to turn 3 decades of anomalous cosmic ray research on its head, a remarkably strong statement from a scientist typically inclined toward careful, measured language. Adding to the strangeness, researchers found that the region just beyond the shock came back noticeably cooler than predicted as well. In a typical shock wave, fast-moving material slams into an obstacle and slows down, converting that lost kinetic energy directly into heat, producing a denser, hotter region on the far side of the boundary. Voyager 1's instruments recorded exactly the opposite kind of surprise, a shock crossing that appeared unusually weak, with a solar wind velocity jump ratio far more modest than a strong, dramatic shock would have produced. The leading explanation researchers settled on was that instead of simply heating the surrounding plasma the way a typical shock would, an unusually large share of the energy released at this boundary was instead going directly into accelerating cosmic ray particles, effectively redirecting energy away from heat and into particle acceleration in a way theoretical models hadn't fully anticipated. Voyager 1's own plasma instrument had already failed by the time it reached this boundary, which meant scientists had to rely entirely on magnetic field data to even confirm exactly when the crossing happened. Watching for the moment, the magnetic field strength suddenly jumped by roughly a factor of 3 and stayed elevated afterward. That limitation made the termination shock crossing even more valuable, when Voyager 2 reached its own version of the same boundary nearly. 3 years later, in the autumn of 2007, because Voyager 2's plasma instrument was still fully functional, giving scientists their first direct, real-time measurement of solar wind velocity, density, and temperature actually crossing this boundary in real time. What Voyager 2 revealed added an entirely new layer of strangeness to the story. Rather than crossing the shock in one clean, single moment, mission scientists recorded at least 5 separate crossings over the course of just a couple of days, with 3 of them clearly visible in the returned data. The shock, it turned out, doesn't sit still. It sloshes back and forth like surf rolling along a beach, driven by pressure fluctuations in the solar wind, meaning a spacecraft approaching it can actually cross back and forth across the same boundary multiple times before finally settling on the far side for good. NASA's Voyager project scientist at the time, Edward Stone, described the overall pattern with a phrase that had, by that point, become something of a running theme for the entire mission, simply noting that Voyager had once again surprised everyone involved. Voyager 2's crossing revealed yet another anomaly, layered on top of the others. Based on Voyager 1's crossing location and standard assumptions about the shape of the heliosphere, scientists expected Voyager 2 to cross the termination shock at a comparable distance from the Sun. Instead, Voyager 2 crossed at only about 84 astronomical units, a full 10 astronomical units closer to the Sun than Voyager 1's crossing, despite the fact that Voyager 2 was traveling through a different region, farther south than its twin. That asymmetry turned out to be genuinely significant, offering some of the first direct evidence that the heliosphere isn't a simple, symmetrical bubble at all, but a lopsided shape, likely distorted by the influence of an interstellar magnetic field that isn't evenly aligned with the Sun's own orientation, pressing harder against one side of the bubble than the other. Taken together, these results from both spacecraft upended what had been a fairly confident, well-established picture of how the termination shock should behave. The anomalous cosmic rays that were supposed to peak dramatically right at the boundary didn't. The shock itself turned out to be unexpectedly weak, rather, then sharp and dramatic. It wasn't even a fixed, stationary boundary, but something that shifts and sloshes back and forth over time. And it wasn't even symmetrical, sitting at meaningfully different distances from the Sun depending on which direction a spacecraft happened to be approaching from. Every one of those findings chipped away at assumptions that had guided heliophysics research for decades before Voyager actually arrived to test them directly. What makes this story worth revisiting is how it set the stage for everything that came afterward. The termination shock crossing wasn't the final word on how strange this boundary region would turn out to be. It was only the beginning. Years later, as both spacecraft continued deeper into the helio sheath and eventually approached the true heliopause itself, they would go on to reveal an unexpectedly thin transition zone, a strange magnetic highway where particles leaked across the boundary in both directions, magnetic field lines that stubbornly refused to change direction the way theory predicted, and pockets of plasma heated to tens of thousands of degrees at the very edge of the solar system. Every one of those later surprises built directly on the same underlying lesson the termination shock crossing had already taught scientists back in 2004 and 27, that the edge of our solar system was never going to behave the way clean, simplified models predicted it would. There's something genuinely valuable in revisiting this earlier, less famous encounter, because it's a reminder that Voyager's habit of overturning expectations didn't start the moment it reached interstellar space. It started years earlier, at the very first boundary the spacecraft encountered on its way there, when a supposedly reliable, near-unanimous prediction about particle acceleration simply failed to show up in the data. Hill's blunt assessment that this could turn 3 decades of research on its head wasn't hyperbole. It reflected a genuine structural challenge to how physicists had been modeling one of the most fundamental processes believed to occur at the edge of any star's protective bubble. Both Voyager spacecraft are, remarkably, still transmitting data today, decades after these initial termination shock crossings first upended expectations, continuing to add new pieces to an already far stranger picture of the outer solar system's true structure than anyone predicted before these 2 aging machines actually made the journey themselves. Every additional dataset they send back continues to test, refine, and occasionally overturn assumptions that once seemed settled, the same way that very first unexpected shock crossing did more than 2 decades ago now. If a story like this, a well-established scientific prediction quietly failing the moment real data finally arrive to test it, is the kind of thing that genuinely fascinates you, go ahead and subscribe. Drop a comment, letting me know what you think scientists still have wrong about the edge of our solar system, and stick around, because these 2 remarkable spacecraft have clearly made a habit of proving assumptions wrong.